Hello class, I'm going to walk through the solutions for group homework for week 9. So for question 1, I put in a red box all of the squares, the perfect squares. So 1 squared, 2 squared, 3 squared, etc. up through 10 squared. So there should be a total of 10 numbers in the red box. All the prime numbers are in orange. And then all the numbers that are co-prime with 42 that are greater than 1. Okay, so I factored 42 over here, and 42 is equal to 2 times 3 times 7. So all multiples of 2, in other words, all even numbers, are not going to be co-prime with 42 because they have a shared prime factor of 2. So you should cross out no even numbers. Also, all multiples of 3 you should not cross out, and also all multiples of 7 you should not cross out. The only numbers that should be crossed out are numbers that, when you factor them, don't have a 2, 3, or 7 in their prime factorization. So all the other numbers that are prime, that are not 2, 3, or 7, are co-prime with 42. So you notice I crossed out every prime number that's 5, and then all prime numbers 11 and higher had to be crossed out. The only prime numbers I did not cross out were 2 and 3 and 7, because those are the factors of 42. The only other numbers that really get crossed out are this perfect square, 25, gets crossed out because its factors are 5 and 5, and there's no 2, 3, or 7 there. And then these two factors, numbers, 55 and 65, 5 times 11, 5 times 13, and then 5 times 17 and 5 times 19. Every other number in this list that's not crossed out has a factor that's a 2, a 3, or 7 involved in its prime factorization. On question 2, this is a rather straightforward question. Not much to say here. You can pause the video and just look at this to see, compare answers. A couple things when I graded. I did not want to see 1s in your triplets because you could turn any of these into a triplet by putting a 1 on it and then make it a quadruplet by putting another 1. You can put 1s on indefinitely. It's not interesting to do that. So I was looking for triplets that did not involve 1s. And then also these factor trees, they don't have to look exactly like mine. It depends on how you got started. For example, if I move this over, I could have done 56 and started by going 8 times 7. And then 2 times 4, and the 7 comes down, etc. So there's different routes you can go with your factor trees. They don't all have to look alike, but what they should all be the same at the end is all the prime factors that you arrive at should all match. So every number has a unique prime factorization, but not necessarily a unique factor tree that takes you there. And then all the counting numbers that have an odd number of possible factors are the perfect squares. 81 is a good example of this. Notice that in this list here, when you do factors, they always pair off, like 1 and 56, 2 and 28, 4 and 14, and 7 and 8. Notice there's always an even number unless it's a perfect square, in which case we have 1 and 81, 3 and 27, but just the 1, 9. So we have 5 factors in this list. So all perfect squares, this kind of thing is going to happen. All right, to determine for number 3, you just have to look for determining whether a number is divisible by 2. Just look at the ones digit, right? If it's even, then the answer is going to be yes. 0 is considered an even number, right? So 2 divides into that last number. For divisible by 3, you just got to add the digits. And so add the digits here, get 20. 20 is not divisible by 3, so therefore neither is 7,526. Add the digits here, you get 18. So this number, 64,215, is divisible by 3. And here in this case, when you add the digits, you get 12. That is divisible by 3. Therefore, this 11,730 is also divisible by 3. To be divisible by 4, you just have to look at the 10s and 1s. 26, in other words. Does 4 divide 26? No. Does 4 divide 15? No. Does 4 divide 30? No. So 4 does not divide any of these numbers. Number 5, you just have to look to the 1s spot. If the 1 spot is a 5 or a 0, then the number is divisible by 5. And that was true only for the second and third number. And to be divisible by 6, well, 6 factors to 2 and 3, and 2 and 3 are co-prime, so you really just have to see if it follows the rules for 2 and 3 both. Well, this first number is divisible by 2, but it's not divisible by 3, so if one of these is a no, then the answer for 6 will also be no. So same issue here, one of these is no, because this number 64,215 is not divisible by 2, it won't be divisible by 6. But this 11,730 is divisible by both 2 and 3, therefore it will be divisible by 6. Determine all possible values of the missing digit. So we were looking for a single digit here, 0 through 9. A lot of people didn't test 0. They tested 1 through 9, but you should also test 0. And if you were to add up the digits, you would get 25 plus the unknown part. And so I cycled through every possible single digit number that I could put here, 0, 1, 2, 3, etc. up to 9. And the only time we got something divisible by 9 is when that question mark was a 2. So that's the only possible value. And then I actually went and did the factoring as well. So 9 times 38,363 will equal this 345,276. To create a rule for 24, for divisibility by 24, I factored to 8 times 3. You must mention they're relatively prime or co-prime. And then it just has to satisfy both rules. So it has to be divisible by both 3 and 8. Thus, the sum of the digits must be divisible by 3, and also the 8 must divide the 3-digit number formed by the hundreds, tens, and ones digits. Those are the two separate rules for 3 and 8. Now, 25 factors, the only prime factors of it are 5 and 5, but 5 and 5 are not co-prime. So we can't use that the method discussed in the lecture to determine if a number is divisible by 25. But if you notice, whenever you do multiples of 25, like 25, 50, 75, 100, 125, 150, 175, 200, etc., all multiples of 25 will end in either 0, 0, 25, 75, or 50. I didn't say those in order, but so you can come up with your own rule for 25. The last 4 digits has to be, the last 2 digits has to be one of these 4 cases. Some people did factor this to 5 and 5, and they simply said, hey, the rule for 5 therefore applies to 25. Well, that's not true, because, for example, 30 is a number that's divisible by 5. You divide it by 5, you get 6, but 30 is not divisible by 25. I mean, you don't get a whole number here. You get, you'll need fractions or decimals. So you can't just say the rule for 5 also works for 25, which a few groups try to make that claim. Let's see, this number here, 2,374, is not divisible by 3, because when you add the digits, you get 17, and 17 is not divisible by 3. Therefore, 2,375 is not divisible by 3, therefore it can't be divisible by 24. However, the last 2 digits are 75, so that does make this divisible by 25. In this case here, 10,152, if you add the digits, you get 9. That's divisible by 3, so that's good. And if you do 8, divide it into just the hundreds, tens, and ones position. So see if 8 divides into 152. And it does. I did the long division here, and I got 19 as the result. Therefore, 8 divides 152. Therefore, 8 divides 10,152. And since 3 and 8 both divide into 10,152, so does 24. But the last 2 digits are 50. They make 52, which isn't 25, 50, 75, or 0, 0. Therefore, it's not divisible by 25. Number 5, the first method is pretty straightforward. I just listed all the factors of the 2 numbers, and the largest one of them that was in both lists was 18. Now, I kind of want to show you, here I did a factor tree, and then anything that was common. I liked some of your student ways to construct these GCFs, like you did color coding, something like this, 2, 2, and 2, and did color coded. And I really liked this color coding idea, 3, 3, 3, and then everything else. Oh, then there's another 3 that maybe I'll make those all green. And so that's everything that's in common, and then that's all you need to put together the GCF, just whatever's in common. So color coding was nice. Also notice that if I were to take the all of the prime factors, including repeats of one of the numbers, and make a set out of it. We'll call that maybe set A, if you will. And then all the prime factors with repeats of the other, call that set B. And there's going to be some overlap, but some distinct. And you can do a sort of a Venn diagram. And so everything that's common would be a 2, and you can make these a little bit larger if needs be. So the factors they have in common were 2, 3, and 2, or just 2, 2, and 3. So that's what's in common. Sorry, 2, 3, and 3, not 2, 2, and 3. And then the only other factor that that's not in common for A is 2. And instead of A and B, maybe I'll say this is the 36 factors, these were the 90 factors, something like that. And the only other one that hasn't been described yet for 90 is the 5. And when you're doing a GCF, a greatest common factor, you just multiply the ones that are in the overlap, including repeats. Right? So 2 times 3 times 3. Okay, for the GCF of 3 numbers, 30, 36, and 54. I just did factors of the 3 numbers and found the largest that was common, that's 6. And to do the factor tree, if you were to do a Venn diagram, I did the factor trees approach. So everything that was common, 3, 3, 3 was common, and it makes 1, 3 here in your construction of your GCF. Then this 2, a 2, and a 2 were in common. That made this 2 in your GCF, and that's all that's common to all of them. To be in the GCF, it has to be common to all 3 numbers, not just some of the numbers. So that was it. 2 times 3. Oops, don't want to do that. Just erase those pink things. 2 times 3 is the GCF. It's going to be 6. If you're to do a Venn diagram approach, I would have the factors of 30, the factors of 36, and the factors of 54. And the ones that were common to both were the 2 and the 3. And then if you were to finish, sorry, by both I mean all 3. So to be the GCF of 3 numbers, it's got to be in all of them. Then what numbers were unique to 30 that weren't in the others? That's a 5. Anything unique to the 36 that hasn't been, looking at the 2 and the 3, but there's a 3 and a 3 in the 54. So we could put one of those 3s here, and then there's an extra 3 in 54 and an extra 2 in 36. Right, so here's, and then here there's just nothing and nothing. Right, those are blank. So here's sort of a Venn diagram approach to looking at all the different factors. Oops, I did some erasing I didn't want to do. Get those back. 2 times 3 will be the GCF. I kind of like this Venn diagram approach because it's going to help me generalize on the second to last question in this homework. Okay, for the LCMs, I just wrote all the multiples and found the smallest that was common, 210. And to create an LCM, you can do the Venn diagram approach. So we have 42 and 70. Okay, what are the factors they have in common? Well, a 7 and a 2 were common. Additionally, the 42 had a 3 involved, and the 70 had a 5 involved. So here's all the different factors and how they overlap. When you do an LCM, you need to not only multiply these factors together, but you also need to multiply everything that's in, really just in all of this. So I'm going to highlight the entire thing. You need to do the factors one copy, mind you. So if you multiply those 4 numbers, 7 times 2, which were common, and then a 3 and a 5, you'll get the 210. When you're doing the LCM of 3 numbers, so I just listed the multiples of the 3 numbers and found that 180 was the smallest of the common multiples. When you're constructing the LCM, look for what's common to everything first, right? So let me go use the highlighter. So this 3, that 3, and that 3 are common to all of them. So you get 1, 3 in the LCM. You know, this 2, and that 2 are common to all of them. So you get a 2 here. And then looking at what's left, anything that's common for just 2 of them, you only need to include once. So 1, 3 there. And then all the leftover scraps, right? The 5 and then that 2 all make the list. Now, the Venn diagram approach here. Let's erase these highlights real fast. The Venn diagram approach would look like we have the factors of 30, the factors of 18, and the factors potentially of 36. What do they have in common to all three of them? Well, 3 and 2 were common to all three. Okay, what's common to just two of them? Well, this green 3 that I'm showing here and here is in the 18 and 36. So there, I'll put that common 3 right there. And then what's left over? What's unique to the 30? Well, there's a 5 unique to the 30. What's unique to the 36? There's an extra 2. And blank, blank, blank. Nothing in those spots. Right, so if you look at this number by number, notice we have all the factors of 30 are right here. 5, 3, and 2. All the factors of 18 are somewhere in this circle. 3, 3, and 2. Then all the factors of 36 are somewhere in this circle. 3, 3, 2, and 2. And when you're doing an LCM, you need to just do one copy of all numbers you see in the union of all these things. So that means we need to have a 3 and a 2, bingo. This 3, there it is. That 5, there it is. And that 2, there it is. And so you can construct your LCM that way. Number 7. So those Venn diagrams will be helpful for understanding what I'm doing here in number 7. Scenario 1, we needed two numbers that have no prime factors in common. They need to be co-prime. So I went with 6 and 35. The factors of 6 are 2 and 3, and the factors of 35 are 5 and 7. So when you do a Venn diagram, in this case, they're disjoint. Right? There's no overlap. When that's the case, they have no prime factors in common. The GCF will always just be 1. And the LCM will be everything in their union. Well, their union is, oops, I wanted that highlighter. The union is this circle and this circle combined. So to multiply all those numbers, 2, 3, 5, and 7, and you'll get the GCF. Well, in other words, it's just multiply 6 and 35. So here's my generalization. If A and B are relatively prime, if they're co-prime, then it will always be true that the GCF of those numbers is 1, and the LCM is their product. You just multiply them to get the lowest common multiple. Scenario 2, all the prime factors of one number, including repeated prime factors, are also prime factors of the other number. Recall that the two numbers must be distinct. So I couldn't just say, put a 6 and a 6 here. I needed distinct numbers. But all the factors of 6 are 2 and 3. Oops. 2 and 3. And all the factors of 30 are 2, 3, and 5. So the factors of 6 are also factors of 30, counting repeats. So if you had picked a number that had, it was 2, 2, 3, then you would need to do 2, 2, 3, and then something else. So that every number here is also here again. And that is what I meant by all the prime factors of one number have to be prime factors also of the other number, counting repeats. In other words, that really just means that the second number, the larger number, is just going to be the same factors of the smaller number with extra factors. In other words, this will be a multiple of that. So scenario 2 is trying to find the LCM, the LCM and the GCF of two numbers where one number is a multiple of the other. And when you do a Venn diagram, in this case, you have a nested situation. You have a subset. All the factors of 6 form a subset of all the factors of 30. Right, all the factors of 6 are right there, 2 and 3, and all the factors of 30 are in this big circle, 2, 3, and 5. And when you realize that the GCF is everything they have in common, the GCF would mean, okay, we'll focus on their intersection, which is 2, 3, which forms the smaller number. So the GCF will always just be the smaller number. And then the LCM will do their union, and you get 2, 3, and 5 will be the LCM. Well, 2, 3, 5 were all the factors of the larger number. So it always turns out to be the following. If B is a multiple of A, and I'm missing a word there, is a multiple, of A, there we go. If B is a multiple of A, then the GCF will just be the smaller number, which is A, and the LCM will be the larger number, which is B, which is exactly right what happens in this case of using 6 and 30. Scenario 3. The two numbers have some prime factors in common, but these common prime factors do not account for all the prime factors of either number. So here's where we wanted a situation where we had some overlap, but also some distinct components of their prime factorizations. So I went with 12 and 20. They share the 2 and the 2, but the 12 has a 3 that the 20 doesn't have, and the 20 has a 5 that the 12 does not have. And so the GCF will be what's in common. So 2 times 2 will be the GCF. The greatest common factor is going to be 4. And the LCM is going to be the product of everything you see in the union. So 3 times 2 times 2 times 5 will be the LCM. And so here's how I generalize this. In this scenario, let's say that set A is all the factors of A with repeats. Right? So if 12 has 2, 2, and 3 as its prime factors, and I think of 2 and 2 and 3 as 3 separate elements of the set A. And set B is all the factors of little b with repeats, if there are any. And then the GCF will be the product of all the factors in their intersection, and the LCM will be the product of all the factors in their union. Okay, so this is probably the most challenging thing. I don't think any group came up with a generalization that was satisfactory to me, but hopefully these solutions will help you see this in a different light when you're doing the LCM or the GCF of two numbers and given these three possible scenarios. And finally, question 8. Question 8 was trying to find a lowest common multiple, because we can't buy partial bags, so we can only get multiples of these bags. So we need to find the lowest common multiple, and that's going to be 120. So we need 120 nails, which means we need 120 bolts, and that means that corresponds to getting 5 bags of nails, but 8 bags of bolts. And in this case here, 64 people and 48 people, we're trying to figure out what's the largest number that divides into both of these. So trying to find the greatest common factor, the GCF. And so I found that using the intersection of the sets of their prime factors, and found that 4 2s was common to all of them, to both numbers. So the product of 4 2s, 2 times 2 times 2 times 2 is 16 is the GCF, which means that's the largest number that divides into both of these. So that's the largest number of people there could be in one row. And so the Marshall band will march onto the field in 4 rows of 16, hence there's 64 people. And the Wentworth band will march out into the field in 3 rows of 16 people per row.